Okay, in the previous lecture, we covered this, and today in this lecture, we will be doing this. So, we'll be talking about optimization problems and classifying them. So, typical structure of an optimization problem is like this, in which you have to say minimize what. It could be maximize also, but then most of the theory is developed with the intention of explicitly minimizing something. So if some objective function appears which needs to be maximized, then you simply say minimize its negative. So typically you will be formulating a problem as minimize a function of alpha and x, in which alpha is in some domain and x is in some domain. Now f is a function. What are alpha and x? Its arguments. Now what is the difference? So the alphas are basically called parameters and x's are variables. What are parameters? Parameters are also variables but treated as constants, okay, which we will not change. And this f is the function to minimize, and it is called the objective function. That is the objective of this entire exercise. So strictly, f is a function of alpha and x, but practically, because alphas will be treated as constants, practically it is a function of x. And x can be many things, giving individual solutions. And the set of all those things that x can be is called the domain. That is from where you will pick up a solution, another solution, yet another solution, and trying to get the best solution. Okay. So, for example, suppose x has three variables, x1, x2, x3. Then if you allow all values of these variables from minus infinity to plus infinity, then you will get the entire 3D space as the domain. On the other hand, there could be some restrictions, okay, in which the domain will be less, smaller. So whatever is the domain, I'm showing that with this capital omega. Now, how do you describe the domain? Okay, so description of the domain is through constraints, which can be of two kinds. It could be an equality relationship equation among the variables, in which case you will call it an equality constraints. There can be several of them, h1, h2, h3, whatever. Together in the vector notation, you could say this. And what equality constraints will do is typically that it will, in effect, reduce the dimension of the domain. That is, in the 3D space, if you give one equation like this, that will basically define a surface. Okay, with different values of the right side, other than 0, you can say 0.1, 0.2, 0.3, 0.4, 1, 7, 19. So you would get different surfaces, like one surface over that, another surface, another layer, another layer, another layer. That would cover the entire 3D space. So the surface, individual surface itself, which you get by putting 0 here or some other constant, is a surface which is actually a 2D entity. So an equality constraint essentially reduces the dimension of the domain. An inequality constraint, where the constraint is defined like this, Gj, G1, G2, G3, etc., that will not reduce the dimension. 3D space will still remain 3D, but you would restrict it to one side of the surface, Gj equal to 0. Gj equal to 0 is a surface, less than equal to 0 will be one side of it. You could have said greater than equal to 0, and some authors and some researchers use the greater than equal to 0 notation, but it is equivalent. As long as you stay consistent, they are equivalent. I have found that using less than equal to 0 for inequality constraints gives certain conveniences in analysis. And majority of the textbooks follow that. So this creates a space restriction. On one side, the domain is there. On the other side, you have infeasible solutions, which is not part of the domain. Okay. So this whole thing in brief, you can say minimize f of x subject to bold h, vector h of x equal to 0 and gx less than equal to 0. So this one line thing is actually equivalent to this whole thing, in which this is described with the help of constraints. Okay. Now we come to classification. First, let us cut down the kind of problems that we will be talking about mainly in this course. Okay. So the main discussion is on the mainstream field of continuous optimization, in which the variables x's are real continuous variables. The objective function f and each of the constraint functions h1, h2, g1, g2, etc. are also real valued functions. Okay. So this is the mainstream field of nonlinear optimization or continuous optimization. Okay, in general. So within that, let us see what different kinds we find. First of all, whether constraints are there or not. That makes a big difference. Okay. So if there are no constraints, then the entire space is the domain. Then you call the problem as unconstrained problems, unconstrained optimization. On the other hand, if there are constraints, equality, inequality, or both, then you will be talking about constrained optimization. And this is going to be more difficult, typically. Okay. Now, between completely unconstrained and constrained with non-trivial constraints, there is a sort of boundary area in which you have constraints, but they are only bound constraints. Okay. And bound constraints, that is, for example, x1 is between 3 to 5, x2 is from -5 to 7, or whatever. So such bound constraints are easier to handle, and sometimes they come not necessarily with the problem, but they come as part of the solution methodology. Because even if there is no constraints in the original problem, sometimes at the start of your solution process, you need to define, or you prefer to define, a region of interest. Okay. So when you go out to look for the best student of 15-year age, then typically, even though not necessary, you say that we are talking about India. Okay. Or you are talking about Kanpur. Okay. Whatever, something like that. So these are sort of bound constraints. I'm not telling that the geography of India is rectangular, nothing like that. But bounds are easier to handle. And sometimes at the time of solution, you prescribe some bounds, which is the region of interest in which you are looking for a solution. Okay. So that typically falls in between in the scale of difficulty level regarding constraints. Now, based on the kind of function which you are minimizing or the kind of constraint functions, if these functions are all linear, then you say it's a linear optimization problem. Okay. And if some of them are nonlinear, even one of them nonlinear makes it a nonlinear optimization problem, which certainly are going to be more difficult. And here also, between linear and nonlinear in general, there is a little, sandwich area in which the objective function is quadratic. Okay, so that is relatively easier compared to general nonlinear problems. And another importance of quadratic case or quadratic problem is that it exhibits most of the important features of nonlinearity without too much complication. And you can, in many places, solve it even without serious methods. Okay. And one more importance of quadratic problem is that even a general nonlinear problem and its function profile resembles a quadratic case in close quarters, because in very close neighborhood, in very close vicinity, a function will be very close to its local quadratic second order approximation. And that is why a quadratic case will typically approximate a general nonlinear problem in close neighborhoods. And that is an advantage. So that is why the quadratic problem, the quadratic case we study with high emphasis. Then there is a third basis of classification, number of variables in X. If there is a single one, then it is a scalar variable. Then you have univariate optimization. If there are many, then you will have multivariate optimization. Again, between a single variable and many variables, there is a sandwich case of two variables. What is so special about two variables? Again, two variable case exhibits most of the important features of multivariate problems, and you can see them in the sense that two variables means you can plot most of the things on the screen and see them. So you can see contours. Okay, the corresponding entity in the case of many variables is called a level surface, which you cannot see on a picture. Okay, so that is an advantage with two variable case, and that is one of the reasons why most textbooks in most examples will pick up two variable problems, and you, the reader, go out with a bad feeling that the author is solving all the small problems and as exercise setting me the tough bigger problems. But the two variable problems are typically taken as examples so that most of the conceptual things can be shown and seen easily. Okay, so two variable problems allow easy visualization of problems and algorithms also. In the plot of a two variable problem, you can see how an algorithm proceeds from here to there, and so on. So from that, you get a sense of how this particular algorithm operates and compare it with other algorithms. Okay. Now, as I have told you earlier, other than this, many different kinds of problems remain undiscussed in this slide, which do not fall in this particular category, which I am calling as the mainstream field of continuous optimization. So many standalone classes of problems remain outside the scope of this classification, and some of them we will study towards the end of the course. Okay, and some of them we will not study because we cannot cover all. Now, this classification, schematically and pictorially, you can see in this. Now, here the picture is a little faint, but let me explain what it is and later download this picture and study it a little properly. So here, three bases of classification. So those three I have put along these three directions. Okay. So this is the direction which is showing the degree of the function. Here it is linear, then quadratic, and then properly nonlinear. Okay. Along this axis, I have shown the number of variables. So that means single variable, two variables, and then many variables. Along this, I have shown constraints. Unconstrained, bound constraints, and then general constraints. So if you try to consider the most general case of this entire picture, then you will have to come to many variables, fully nonlinear, and with constraints. So you will reach this zone, which is nonlinear optimization problems. Okay. Now, a special case of this will be linear optimization problems here, in which everything is linear. Another special case of this will be at the bottom, unconstrained optimization, no constraints. Now, if you go both ways towards the simpler, this way also and then this way also, then you should reach this corner where there is no problem. Why? Because if you have a linear function and you have no constraint also, then there is no scope of optimization, because in some direction, as long as you go on reducing the function, linear function, you see. In another direction, as long as you go on increasing the function. So function is unbounded on both sides. And there is no constraint, so nothing to stop it from going unbounded to minus infinity or plus infinity. Okay. So there is no problem here. Here it is linear programming. Here it is unconstrained nonlinear optimization. And when there are constraints of all kinds and the functions are also nonlinear, then you have this. This is the real problem. Okay. These are also two real problems which we will be handling on the way. This is the final thing that we will be targeting, nonlinear optimization problems. And here you will have two variable problems, which will often come in examples. Here you have single variable problems, which is important. Okay, very easy in a way. In the scale of the whole thing, it is very easy, but it is important because it has its own important place in the solution of general problems also. Okay, and if you leave this narrow strip behind, then next you have bivariate problems, two variable problems. Okay, and here you have quadratic problems, which are also important, which we will be seeing. They are not very difficult, but not very easy either. Quadratic problems of many variables. Single variable, there is nothing. Okay. So in the picture, you see all the problems in their respective locations. I suggest that you download this picture and study it a little properly, and then place in that picture mentally where are where is each thing that we will be studying in the course. Now, methodology of optimization. How you typically handle an optimization problem from start to finish. The starting step and the final step fall in the area from the field from where the problem comes. Rest of it is the matter of optimization. Okay. So first of all, from the knowledge of the problem field, you identify the elements to define the optimization problem. This is formulation. Okay. Quantities, this is the basis of the formulation basically. Quantities you can change to improve the solution. These quantities are called variables, as we discussed earlier. Quantities you could change but have decided to keep unchanged for the time being. These are called parameters. Then the criterion dependent on these parameters and variables that you want to minimize or maximize. And this you call as the objective function. And then equations and inequalities in the variables and of course parameters that characterize the domain of acceptable solutions called feasible solutions. Okay, so these are constraints. So these things you identify from your knowledge of the field of the problem, from where the problem has come. Now assemble these things in this manner in the form of the standard problem, which you will now solve. So in order to solve that, you apply an appropriate optimization algorithm or method. At the end of it, hopefully the algorithm takes you somewhere and you get, upon convergence, you get an optimal solution. At least you think so. Okay. Because you expect the algorithm to have worked properly. Okay. Now this optimal solution, which you have got in hand, you should always verify it through something called optimality criteria. There are optimality conditions on problems, and on that you should check this solution whether it is fine, whether it satisfies the optimality conditions. Suppose it does. Otherwise, there is some problem with your application of the method. Now, if it satisfies the optimality criteria, optimality conditions, that means you have done a good job here. Okay. Then post-process the results and study them. Maybe you will plot graphs, and you will also perhaps plot the results of different iterations of the algorithm and study how the algorithm has progressed and so on. After this, your task is not over. You estimate the sensitivity of the optimal solution and optimal functional value to the parameters which have been maintained constant as of now. Okay. So parameters are things which you could have changed, but just because your boss has said that, well, working hour in our office is 7.5 hours, so you have kept it constant. Now, if it is made 7 hours or 8 hours, then how productivity would change, you could study that. Whether, I mean, if one day your boss says that advise me whether I should change the working hours, then in order to advise that him on that, you need to be able to change it and see. Okay. Sometimes even without actually changing, you could estimate how the optimal solution would change if you change some parameters slightly. And that study is called the sensitivity analysis. So estimate that sensitivity. If the sensitivity is high, that means changing this thing a little bit may result in gross advantage. Okay. So in that case, if you have control over the parameters or try to assume control for that matter, once reconsider a revision of the formulation, possibly treating such influential parameters as variables instead. If the sensitivity is low to some parameter, then you can leave it as parameter. Doesn't matter. Even if you could change. How does it matter? Suppose, okay, now if you make a revision, then the earlier steps you have to repeat. Earlier 3 steps. Now, examine the final optimal solution after it has come through these things for utility. Now you go back to your field from where you picked up the problem and check it with that. How good is the solution in the physics or in the application or in engineering of the thing? You then check this final optimal solution. Okay. This will involve the subject background from where the problem came. And sometimes some conceptual oversights, actually what you call as silly mistakes in formulation, get caught at this stage. Okay. So if something like that happens, then go back to item 1, reformulate the problem and repeat the entire process. This is the entire methodology that you will be following if you apply optimization in some of your work, in academic or in industry, anywhere. Okay. Now, let us summarize what we discussed, okay, in this lecture. So, an optimization problem typically has a structure involving variables, objective function, constraints, etc., which needed to be clearly identified. Okay. Now, optimization problems come in a wide variety, and different classes of them often need different treatment. This makes it a little involved, difficult, and big area. Okay. And that is one reason why whatever you do in optimization, that is going to cover only some segment of the entire field, as this course will do. Now, following the systematic discipline of taking an optimization problem from start, genesis, to the acceptance of the final solution is important. It's a process which needs to be followed properly. Otherwise, you might end up spending a lot of effort to do something which is not great, and or it doesn't make even sense at times. Okay, so this is something which you will learn more, you will understand better when you apply optimization knowledge in certain fields. Okay, so in the next lecture, we will be discussing optimization algorithms, a broad overview of them. What are the key elements in those algorithms? Okay, thank you.